Hey everybody, welcome to the Steam Distillation Lab. Here's the outline for this video. I'll be going over the experiment in general, focusing on the steam distillation technique. Then I'll show the experiment in the lab, and at the end I'll be going over some NMR concepts. In this experiment, we are going to be steam distilling cinnamaldehyde from ground cinnamon, so I'm going to spend some time going over that technique. In steam distillation, we are able to separate volatile organic compounds from leaves or seeds or even like inorganic salts just by boiling them with water. And the reason this works is because when two immiscible compounds are placed together, their vapor pressures are actually additive. So in this case, we will have cinnamaldehyde, the organic compound, that isn't very miscible with water, and the total vapor pressure of the system of the two-phase mixture will actually be the sum of the vapor pressures of each pure compound, the cinnamaldehyde and the water. Since the total vapor pressure is higher than each compound's respective vapor pressure, both the cinnamaldehyde and the water will co-distill at a temperature that's actually lower than water's boiling point. Here's an example of how this works using iodobenzene, which has a boiling point of 188 degrees Celsius. Its vapor pressure at 98 degrees Celsius is 46 torr, and the vapor pressure of water at 98 degrees Celsius is 714 torr. Together, those add up to 760 torr, which would be equal to the atmospheric pressure. So this compound will co-distill with water at 98 degrees Celsius rather than its usual boiling point of 188. So this is a huge advantage when using steam distillation because it allows us to distill organic compounds without decomposing them. In our case, cinnamaldehyde has a boiling point of 248 degrees Celsius, but it decomposes at that boiling temperature and it can oxidize into cinnamic acid. Instead, if we boil it with water, it will co-distill at the boiling point of water or even slightly lower. Another cool aspect of steam distillation is that we can pretty easily separate organic compounds directly from their source. And this is what essential oil companies do all the time. For example, limonene is an organic compound that gives the fragrance of oranges and is often used as a flavoring agent as well, but it can easily be separated from orange peels using steam distillation. In our experiment, we will be checking out a 50 milliliter Erlenmeyer flask with a specific joint that can attach to the Hickman still, and you can just grab that from the stockroom. Then we'll add the ground cinnamon to about 10 to 15 milliliters of water and begin boiling it. And we'll also be using Triton X45 as a surfactant since it lowers the surface tension, helping the water boil not as violently so that we don't get cinnamon up into the Hickman still as well. Here's a look at that compound. The N here representing a given number of ether groups attached together in a chain. So for Triton X45, there would be on average between 4 and 5 ether groups attached together. And with that many oxygens, Triton X45 is pretty water soluble, so it won't contaminate the cinnamaldehyde water distillate that comes off during the steam distillation process. As the mixture boils, a milky cinnamaldehyde water distillate will start to gather in the Hickman still. So the water and cinnamon will be boiling in the Erlenmeyer flask, and the distillate will start to rise, condensing and gathering in the base of the Hickman still, and then we can remove it from there using a Pasteur pipette. We'll gather about 5 to 7 milliliters of that distillate into a separate test tube. Then we'll extract cinnamaldehyde out of that distillate using methylene chloride, and we'll do 3 extractions. Then those extracts can be dried with sodium sulfate and the solvent evaporated. This will leave us with a pure cinnamaldehyde product, which we can weigh to calculate a percent recovery. We won't be calculating a percent yield because we didn't do any reaction with mold-to-mole ratios to worry about. So the percent recovery will just be the weight of cinnamaldehyde isolated divided by the weight of cinnamon used multiplied by 100. And finally, we'll characterize that product by running an IR spec. Okay, here is the Erlenmeyer flask rented from the stockroom. I've already placed a spin bar inside, so now I'll add between 10 and 15 milliliters of water. Then I'll add 10 drops of the Triton X45, doing all of this before adding the cinnamon because adding the cinnamon last can help keep it from burning on the bottom of the flask initially. Now I'll weigh out about 2 grams of the ground cinnamon, noting exactly how much is weighed so a percent recovery can later be calculated. And I'll just add that on top of the water in the flask. Now I'll set up the apparatus, attaching the Hickman still and a water condenser on top of the Erlenmeyer flask, and then start heating things up. As it does warm up, you can actually start to see the milky distillate in the cinnamon, and as that begins to boil, we're going to see that a lot more on the sides of the flask. Eventually, the distillate will start to condense in the Hickman still, and when the base fills up, we can begin gathering it using a pasture pipette. Be careful to monitor the cinnamon because we don't want it boiling up into the Hickman still. So if it starts getting close, lab air can be used to cool the flask down. Right now, it's actually not an issue, but I just wanted to show what to do if it did start boiling too violently. It looks like enough distillate has gathered in the Hickman still now, so I'm going to go ahead and start removing it and transfer it over to a test tube. I'm going to keep doing this until I've gathered 5 to 7 milliliters of the distillate, and I have a separate test tube filled with about 7 milliliters of water as a reference, so I'll keep going until it matches that. After doing this about 8 or 9 times over 20 minutes, I think I'm on the last one and it should match up with the water level. Now I'm good to move on, so I'm going to start getting some methylene chloride to do the extractions. But before adding it to the test tube, I'm going to rinse the apparatus to collect any cinnamaldehyde that would be adhering to the glass surfaces. Then I'll just remove that from the Hickman still and add it to the test tube containing the distillate. Now we can see the organic phase below the aqueous one, so I'm just going to add a little bit more methylene chloride, mixing the two phases together really well, and then transfer the organic phase over to an Erlenmeyer flask. Before moving on to the extractions though, I'm going to start working on cleaning up the apparatus so that the remaining cinnamon doesn't completely coat and burn onto the bottom of the flask. I'll add a little bit more water and keep it warm on the hot plate, scraping the cinnamon off of the bottom of the flask, and then disposing of it in a bucket specifically designated for the cinnamon waste. You can see that there is still some burnt residue on the bottom of the flask that I'll need to clean off, so I'm going to add some more water and add about a gram of sodium carbonate and heat up the solution to help remove that burnt residue. The solution can be allowed to boil, but be careful because if there's still a good amount of cinnamon left, it can actually boil over and come out of the flask, so just monitor it and don't leave it there. And a spatula can be used to help scrape off the burnt cinnamon. And this should be continued until the Erlenmeyer flask looks just as clean as it was initially. Now I'll continue with the extractions, adding methylene chloride, mixing the two phases, and transferring the organic layer to the Erlenmeyer flask, and I'll do this a total of 3 times. Once the extracts have been gathered, I'll dry that organic phase over some sodium sulfate, and I'll add that until it's free flowing. Then I'll transfer that solution over to a beaker, and since I used quite a bit of methylene chloride, I'm transferring it to a beaker rather than a conical vial, although a conical vial would probably be preferred. And I'll rinse the sodium sulfate with some additional methylene chloride to help reclaim more product. The solvent can then be evaporated using a stream of air and gentle warming until just the cinnamaldehyde liquid remains. I'll weigh out the full beaker containing the isolated product and use that to spot a salt plate so that an IR spec can be run. And that turned out really well. There are a wide range of peaks identifying the product. We have the aromatic hydrogen peak at 3335, a group of peaks above 3000 for the hydrogens attached to the alkene, the two aldehyde peaks at 2814 and 2742, a carbonyl peak at 1677, and a peak at 1626 for the carbon-carbon double bond. Finally, I'll weigh out the empty beaker to get the weight of the cinnamaldehyde isolated. Okay, I wanted to go over a few things that should be helpful when analyzing the NMR spectra for cinnamaldehyde. The first thing that we should recognize is that this molecule is fully conjugated and there's going to be lots of resonance that will actually have a pretty strong effect on how shielded or de-shielded the hydrogens and the carbons end up on this molecule. So let's go ahead and consider those resonance structures. The carbonyl group would be electron withdrawing, so electrons would be pulled onto the oxygen to form this first resonance structure. Then the double bond next to it will compensate by moving over to form this resonance structure. And then we can just continue down the molecule, moving the pi bonds over and continuing to draw the different resonance structures. As we do this, we can see that certain carbons have positive charges placed on them. So if we look at the hybrid structure, any of the carbons that had a positive charge placed on them in one of the resonance structures would now have a partial positive charge placed on them. This means that these carbons and the hydrogens attached to them would be more de-shielded because they have less electron density around them to shield them from the applied magnetic field. So for example, if I look at these two hydrogens attached to the alkene, this hydrogen would actually end up being more de-shielded because of that partial positive charge, even though the other one is closer to the carbonyl group. The same principle can apply to the hydrogens on the aromatic ring, but make sure to use all the other tools to analyze the peaks and identify which peaks go to which hydrogens. I also wanted to go over some concepts that have to do with splitting. So to do that, I'm going to look at this example from the post-op questions. And I'll be focusing on hydrogen 5, so we can simplify it and just look at it like this. Hydrogen 5 has two neighbors, so we might assume that it would end up as a triplet, but something else is actually happening here. If we look at the two neighbors, hydrogen 6 would be cis to hydrogen 5 across that double bond, and hydrogen 7 would be trans to it. Since hydrogen 6 and hydrogen 7 are unique enough from each other, they would actually have different coupling constants and would each split hydrogen 5 differently. To show this maybe a little bit easier, let's take a look at the splitting tree for hydrogen 5. Hydrogen 5 is split a certain amount by one of the hydrogens, and that distance is called the coupling constant, represented by the letter J. In this case, this would be the coupling constant for the trans hydrogen, which usually ends up being between 12 and 18 Hertz. Then hydrogen 5 is split once again by the other hydrogen, and this distance would now be for the cis coupling, which usually ends up between 6 and 12 Hertz. Since the splitting for trans hydrogens is a lot wider than the splitting for cis hydrogens, we don't end up with a triplet. As we can see here, there are 4 distinct peaks that would be formed. So if we look at the HNMR, hydrogen 5 would end up looking like this, and we call this a doublet of doublets. From this, we can actually calculate the trans and cis coupling constants using the ppm values for each peak. So I'm going to go ahead and transfer those numbers to the bottom of the splitting tree that we created earlier. And then if I wanted to calculate the cis coupling constant, I would just need to measure this distance here, and I could do that by subtracting this number from this one. Or I could subtract this value from this one because that distance would be the same. Then we can find the coupling constant for the trans hydrogen. The problem is there's no value below this line, but it should be right in between these two numbers here. So we can just find the average between those two and then do the same thing on the other side, finding the average between these two numbers. Once we have that, we can then just subtract this value from the other to get the trans coupling constant. Or we could recognize that this splitting here would be the exact same as this one, meaning that this distance is identical to this one. Therefore, if I wanted to calculate the transcoupling constant, I could just subtract this value from that one, or do the same thing on the other side, subtracting this value from that one. Now, we'll want these coupling constants in the standard unit of Hertz, but currently everything on the HNMR has been converted to ppms. And this is done by taking the frequency of the signal in hertz and dividing it by the applied spectrometer frequency in megahertz, therefore parts per million, because megahertz are 1 million times the magnitude of hertz. So if I wanted to get this signal back to hertz, I could just take the ppm value given and multiply it by the spectrometer frequency, which in this example would be 300 megahertz. Now I'm going over this splitting because the same thing is going to happen on cinnamaldehyde. If we look at this hydrogen here, it sees this neighboring hydrogen across a double bond, but it's also coupled to this one because it's on a neighboring carbon. And since these two hydrogens are fairly unique, they'll each have different coupling constants and will each split this hydrogen differently. So if we look at the HNMR for cinnamaldehyde, that hydrogen will actually end up as a doublet of doublets shown here. And that's all I'm going to go over. I'm going to leave the rest of the peak assigning to you now.